We'll move on to the next presentation now, which is from Elena Dominguez. Elena, are you there?
Yes, I am.
Hi, Elena. Good to see you. Okay, just to introduce Elena, she has been a safety consultant with Pilz Automation Safety in the USA since 2007. She has an engineering degree from General Motors Institute in Flint, which is in Michigan. Is that right?
Michigan, yes.
Okay, and has spent 25 years in robotic integration with Chevrolet, ABB, and Rimrock. She participates in both the US and ISO committees for industrial robot safety, and her expertise and work covers risk assessment, functional safety analysis and design, validation of safety systems, and evaluation of compliance of safety systems. And I met Elena through the TC299 WG3 group, and personally, she has helped me so much to understand some of the more technical aspects, and I find her work fascinating. So I look forward to this, Elena. If you're ready, I'll hand over to you.
Okay, very good. I will share my presentation now. So let's see. Oh, I always forget to hit that share button. There we go. Very good. Can you see my presentation now?
Yes, we can. Thank you.
Oh, very good. Well, thank you for the invitation, both to you, Sarah, and you, Isabel, for inviting me to speak here. It's been quite interesting. I bring here the engineering side of the more traditional approach of robotics and safeguarding. But what
Thank you for being here, Elena. Thank you.
Thank you. So in collaborative applications, what happens is we have to adjust safeguarding in robotics in the industry sector because of the changes that collaborative robots are bringing. As you know, as has been told in a number of presentations, that collaborative robot systems have benefits, but that brings new challenges in robot safety. Now, one acronym I'll use now and then is HRC, Human Robot Collaboration. That's just talking about the robot collaborative applications that we've been speaking of. The benefits come from a very high degree of a human and robot interaction, as some speakers spoke of. You can automate portions of a cell that you couldn't before because of the constraints of traditional robot safeguarding, where you have a perimeter, a cage around the robot. Now you can place robots in closer proximity with people, and you can in fact have the robot work real time with the person in the same safeguarded space, in the same workstation. However, that brings new challenges because now people are interacting with a moving robot and there are no barriers separating them. So what the one thing that I've been listening here is that I'm talking about physical harm, the protection from physical harm. And I see that as an underlying foundation for human trust. If you think that robot's going to hurt you, you're not about to trust that robot. So this is the starting point, and the people here are taking it on to the next level. Now, to safeguard a robot, you have to look at it in a more in-depth engineering view. In the past, you just had to put a fence around it, put in an interlock door, and stop all motion when you approach the robot. However, now we have a moving robot. So in this application, we have to try to predict contact events. When and where might a robot strike someone? We have biomechanical limits that we want to respect to avoid injury. We're looking at the designs of tools and fixtures and parts now, and the geometric contours that they have to avoid injuries. We're looking at safe speeds and the calculations and predictions of that, and setting a multitude of new safety parameters. With that, that comes about because of the collaborative robots that are now defined in the ISO 10218. Well, I shouldn't say now, it's been 10 years. There are 4 methods currently identified: safety monitored stop, where someone approaches the robot and it comes to a stop, yet it's still powered up and ready to move at a moment's notice. Method 2, hand guiding. As you saw, you grab the robot tool or the part and you apply force, or you hold the control and you move the robot. But once you release the control, the robot will stop. Method 3, speed and separation monitoring, which is the hardest application, but there are some applications such as biorobotics that are looking at making this reachable in industry outside of the lab. And then method 4. Method 4, this is the application that industry in general is looking at, where they're focused on using these types of robots at this point. They're smaller robots set up with small motors or control systems that will control the forces and the speeds and the reach of the robot to keep the operation safe. The big difference here with method 4 is here contact may occur. Now you have people actually interfacing with the robot while it's moving, while the other 3, the robot had stopped. In addition, of these methods, typically there'll be a combination of these methods, whether you control the speed and slow it down, or adjust the force, or bring the robot to a stop. Now, in doing this, the essential thing you have to do that is mandatory in the robot safety standards of today is that you perform the risk assessment, and we've talked about that. This is the ISO 12100 model, where you look at risk as a function of the potential severity of injury, or here I should say severity of harm, and the probability of occurrence of that harm. Since probability of occurrence is hard to predict on a piece of paper, without any history, we look at 3 factors: the exposure of the person to the hazard, the occurrence of a hazardous event, something fails, somebody does something they shouldn't do, and thirdly, the possibility of avoiding that harm. So you take that concept and you apply it to the risk assessment of a collaborative system. But as I said, one of the essential things that's new here is that we have to realize that there will be contact events. There will be crush events and impact events. Situations where the robot presses the operator against a fixed object, and situations where the robot passing through a path in free space will contact that person at a given speed and momentum. So these contacts will occur. Human nature is people will get in the way, either intentionally or unintentionally, depending on the application. So that just complicates the requirements for safeguarding the robot. Now, the good thing is we have some data to work with. As an engineer, I love data, I love information, I love guidelines. So what we have in a ISO TS 15066 document is that it establishes some initial biomechanical limits, that is, limits related to the human body and what it can take, that define force limits and contact pressure limits along different body regions. So with that, we have a chart. This is only half the chart, by the way, so it's missing a few pieces of body regions that are common. But the first thing you notice that it says, hey, if it strikes me in the chest, if it strikes me in the head, these are the associated limits. It breaks up this table with the contact type. As I said, there were 2 types. First of all, there's the crushing, in which case it's labeled as quasi-static here, meaning that if the robot presses against a person for a sustained period of over a half a second, then these initial limits apply. If the contact is quick, say the robot strikes you in mid-space and you fall away, or if the robot presses you against a fixed object but then retracts right away and you have an impact of half a second or less, then that is referred to as the transient biomechanical limit, which case now you have for each of these categories two parameters that we look at. One is permissible force. Permissible force is based on injury data from medical literature. How hard can the robot push against someone and not exceed the minor injury threshold to the point where simple first aid, whether it's a simple Band-Aid or just some time, will allow the person to recover without any lost time. In addition, there's contact pressure. Besides the force being applied, how big an area is that force applied on the human body? So we know if we take a dull surface and push it against the human body within the forces allowed in the previous columns, you're fine. But if you sharpen that edge and push it against a person within the allowable forces, now you start to cut the person. So contact pressure must go hand in hand with forces as we design a system. So these limits, specifically quasi-static force and pressure limits, are limits that are sustained for over half a second. And the transients are for forces and pressures sustained for less than half a second. The forces are based on a minor injury threshold, while the contact pressure instead is based on a threshold of pain. The reason being that with contact pressure, you're going to feel pain first. It is the leading indicator as to where you are in the level of contact pressure. So in this table, it established that as a design guide as to how to design the tool so that if you can stay at or below the threshold of pain, you will definitely be below the minor injury threshold. So now we have data to design our systems. However, in our risk assessment, we have to define the potential contact events, regardless of what application you have with a robot. Now with the interactions of a collaborative robot, there's going to be contact. So where is it going to be? So in this case, I identified 3 different situations where I see potential contact. In an application like this, we have a robot that's picking up parts and building a pallet. In a typical job, I'll find anywhere from 5 to 20 types of potential contact points. Here I just show 3. At each one, you got to decide, is it going to be a crush or an impact? Because remember, the duration of that force or contact pressure is going to require the selection of a different biomechanical limit. Therefore, you have to identify what type of contact it is. You also have to define the body region, because the body will vary in terms of vulnerability. Someone's hands will typically take more force than, say, my forehead, because I'm used to dealing with my hands and receiving a hit here and there as I do my work, but I'm not used to banging my head against the wall. So some days it seems like I do that often. But in addition, you have intentional, or as I say here, reasonably foreseeable misuse. In this risk assessment, you're going to need to ask the question, what is the human person do? What is the human doing? If I tell them not to go in a certain area because of an increase of contact, will they do it? Most of the time, maybe 9 out of 10 times, but every now and then somebody may do something because you've identified a motivation for them to break the rules. So that goes into the assessment. Now, the goal of the assessment is for this collaborative application to be safe. So we identify the protective measures to lower the risk, the initial risk of the cell, down to something acceptable. And running at an acceptable level of risk should give us a good safety record. The typical thing that's done in industry now is they'll use a proven risk methodology to guide the user as to what protective measures are necessary and how many. At the end of the day, once you have experience running a cell, a good safety record is going to confirm that you've reached that level of safety. In this case, I just show a graph out of the ANSI RIA TR 15.306 robot risk assessment methodology, where it shows a graph where you estimate the risk, and it shows some guidance in terms of what protective measures should be applied based on the initial level of risk. So how do you safeguard it? You apply a risk assessment methodology that you know it works, and you keep applying protective measures until you reach that acceptable level of risk. So say you have an application, you identified a contact, a potential contact point, and you feel it's going to be over. So there's these risk reduction measures that have to be applied. There's active measures that are currently available with the technology we have, and we have passive measures. So first of all, on active measures. If I have a robot that has a safety rated control system that can adjust forces or speeds or the space, which is essentially the reach of the robot and the movement of the arm, I can adjust those parameters and reduce those forces or speeds to get down to below the biomechanical limits that we've identified. There's also defensive programming. Maybe I can move the robot such that I can move the hand of the robot to a position where there's less exposure to certain surfaces or certain speeds or crushing points in the cell. I can apply safety devices. Typical thing is to put a laser scanner, that's a presence sensing device that would detect people approaching the robot. And as they approach the robot, we could implement some lower speed limits to slow the robot down to what is an allowable speed, up to the point where we could actually stop the robot. Or maybe we'll have a skin on the arm, like was shown on one of the applications, where if you contact the robot, it'll come to a stop. So those would be active measures. Final thing you could do is just relook at the cell. How can I eliminate a certain degree of interaction to get it down to an acceptable level of risk? And then on passive measures, here are things that don't involve the control system or the programming. I can soften the edges and corners of the fixtures and tools so that there's no concern about laceration injuries. I can put padding on the cell to cover those sharp corners, or perhaps to absorb some degree of energy. And I can make mechanical elements that are compliant, put springs or collapsible joints so that when there is a contact, the tool applies less force. Speed limits. So how fast should I allow a robot to move as someone is around it? There are some approaches now with formulas and calculations that you can take to predict how fast a robot should go. There's two situations. One is contact in free space, where you can look at the two masses, the mass of the robot and the mass of the human body region that's being contacted, and the stiffness of the human body in that area, and calculate an allowable speed. There's even a chart in the ISO TS 15066 to use based on the how big the robot is and where it strikes the human. In addition, you also have the same situation on crushing events, except that the human becomes part of the fixed object. So it's the robot and the human body stiffness that are relevant in the calculation. But from this, you can say how fast should the robot go. So this is an added step beyond what was traditionally necessary. Contact surfaces, as I said before, we used to not care because the robot would be stopped. Now the robot's moving. So do I have a sharp corner that can cause a cut, a deep cut on my arm? Well, let's round it out. Let's put some padding on it if we can't round it out. But this is new in terms of designing robotic systems that wasn't necessary before. Finally, we have administrative measures. We have to warn people with signage and warning signals. We have to instruct the people, train them on how to safely work near the robot, and enforce their behavior so that we minimize incorrect interaction with the robot. Finally, the last thing is validation. Any safety system you put in has to be confirmed in terms of its effectiveness to provide its protective properties. So you're going to confirm the effectiveness of the protective measures. And in collaborative robots, you have to look at forces. So you're going to take a special force measurement device and measure forces. This measurement device would simulate how the body reacts and what forces the body would feel. In addition, you apply a technology to measure contact pressures to see, are there surfaces and edges and corners that have to be rounded out or padded because they exceed the pressure limit? So you would also make measurements on that. At the end of the day, any safety system needs to be validated before it's turned over to the normal operations and the personnel running the system. So in summary, collaborative applications require engineering to engineer safety into the design. The typical collaborative robot is not guaranteed safe out of the box. You have to perform your risk assessment, analyze the system, design in the safety necessary, and then at the end, validate that the safety has been correctly reached in the application. So one thing I want to add here is that this is still in its infancy as far as understanding physical harm effects. There's going to be other things we have to look at, repeated exposure to pain. If I'm constantly feeling pain, even though I'm not injured, at some point that's going to have an effect. And I think more of a psychological one perhaps, but that has to be looked at and addressed in the future as we start collaborating closer with robots. And then we have to look at accumulated stress versus single injury events. Right now, we're focused on the single injury because that's been the nature of machinery with respects to humans. But now we are going to have a robot that's constantly there. And do we have accumulative effects that we have to worry about? So there's still areas, I believe, that will have to grow in terms of reaching a safe state. So there we go. Please, if you have any questions, let me know.
Thank you, Elena. Fabulous presentation as always. And I'm really glad that you presented all of that because as you pointed out at the beginning, the physical safety is fundamental. I mean, I can waffle on about the psychological safety, but it's nothing without, you know, it's so related to the physical, and what we do is build on those those parameters and those, you know, engineering approaches that you begin with. And that's fundamental. And it sort of aligns as well with what Kevin said about without human accurate perceptions of safety, of their safety, then there's no, that's fundamental to acceptance essentially. So really important what you do, and I really appreciate that. So do we have any questions for Elena? Isabella, you're going to start.
I'm not going to ask. I'm just going to say that it was great to have this presentation. To thank you so much, Elena, and that we had the chance to see how risk can be managed really from a human-centered perspective. Of interaction with these robotic structures, and it's really very good. Thank you.
Well, thank you. Like I mentioned, now that we take away the fence, now people are free to roam. So at the end of the day, as an employer, the employer still has the responsibility for a safe workplace. So therefore, you ignore what the human is going to do around the robot. You have to address it so that at the end of the day, 10 years after this robot's been in operation, you still have a good safety record on the system.
Yes.
Okay. Do we have any questions for Elena?
I had one question.
Yes, please, go ahead.
Do you have any comments about using camera-based systems for workspace monitoring, either for speed and separation monitoring or other safety relevant features in the robot cell, or perspectives that would look in the future?
Definitely, technology keeps moving. We started off with the basic tools that were in place, which was safety sensors that are pretty normal applications in the traditional robot cells, such as laser sensors. And we've propagated to safe motion control that allows us to control speed and torque with the motors to achieve the force and speed limits. And now there is a lot of good work in terms of these more sophisticated sensors. There's a new concept called sensor fusion, and a lot of work is going into that, not only in robotics, but other areas, to where you take a traditionally non-safety rated system, such as a three-dimensional sensor. You make the systems redundant, whether it's the same sensor or a different sensor, and you have the safety controller take that non-safety rated data that is diverse and redundant. You determine the diagnostic coverage to come up with a performance level for that that's equivalent to what we can buy off the shelf for traditional safety systems. So the limitations of purely safety rated proven devices is going away. There's and the more sophisticated systems such as speed and separation monitoring is now being able to be implemented because of the fact that we can start using this new data and still achieve safety rated, functional safety, predictable reliability to maintain the safety of the cell.
Is that okay, Kevin? Okay.
Great,
Do we have
thank
any
you.
other questions for Elena? No?
No problem. If you have questions, my phone number are there. Please reach out.
Yeah,
It's been exciting here with the new changes. And new
good.
technology.
Yeah, and I hope you see that what you do is fundamental, and that there hopefully there'll be some, hopefully in the future, some parameters on psychological safety in the same way that you look up the, you know, the quasi-static and static, you will look up those parameters for you know, for force and force limits now.
Yeah, I think
I hope so, yeah.
it's going to be part of the mix.
It would be.
What we are doing.
Of course, as we pointed out, some of those are quite difficult to achieve because, you know, anything that involves people. Were you, was life a lot easier when things were fenced off?
Yes.
I imagine so. Okay. Anybody else got any more questions before we say goodbye to Elena? All right. Thank you, Elena. Thank you so much. It was really interesting. Thank you.
Thank you.